Hello class, this is just a continuation for applying series concepts to different problems. Once again, we just need to summarize the information given in the question so we can know what to work towards, and also understand that the questions can vary drastically, so these are not all the types of questions we might find, but these are just two examples and focus more on the thinking rather than the solution itself. So here we go. So we have some series, and we're being told that this is a geometric series, 3x 27 over 4, and so on. So we will definitely have a common ratio, but we now need to calculate the sum of the first 10 terms. The tricky part here is that we don't know what the common ratio is, but we can still calculate it. So here we go. If we take the term x and we divide it by the previous term, 3, it should equal to 27 over 4 divided by x. If we continue working with this, we get x over 3 is equal to, this will become times 1 over x. So we get 27 over 4x. Okay, cross multiplying this, we get x squared equals 27 times 3. We'll get this, 27 times 3, 81. We get 81 over 4. Taking the square root of both sides, we get x is equal to plus or minus square root of 81 is 9, square root of 4 is 2. Okay, so now this becomes a lot trickier than we expected. So we could have two possible geometric series. We have 3, 9 over 2, 27 over 4, or we could get 3, negative 9 over 2, and 27 over 4, and so on. So from here we can see that the common ratio, this one, would become, well, 9 over 2 divide 3. We get 1.5. So we could have a ratio of 1.5. Or for this one, we could have a ratio of, well, if you do negative 9 over 2, we get negative 1.5. So there's actually two sets of answers that we might encounter here. Well, now we can just merely apply both answers to the sum of a geometric series. I hope you remember it. It's S of n equals a r to the power of n minus 1 all over r minus 1. So applying the positive first, we get S of 10, that's the first 10 terms. We get a, 3, bracket, 1.5 to the power of 10 minus 1 all over. I'm going to skip a step here. R minus 1, it's going to be 1.5 minus 1, which is 0.5. Substituting into our calculator. The sum of the first 10 terms, let's leave it as a fraction. You know what, let's just do it as a decimal. Should be 339.9902, and we can approximate this to 340, just about there. Now, a common mistake some students would make here is that they believe that because the ratio is negative 1.5, they might believe that the answer will be negative 340. This is not the case. And we'll prove it just by finding the sum of the first 10 terms. So S of 10, actually, fortunately I have an iPad and I can be lazy here. I'm just going to duplicate this. And I'm just going to change that value there. It's going to be negative 1.5. And the denominator is going to be negative 1.5 minus 1. So substituting into our calculator, 3 outside of negative 1.5 to the power of 10 minus 1 all over negative 1.5 minus 1. This will give us negative 67.998, which we can approximate to negative 68. And we can use the fractional values here, but hope you get the main idea here. So normally you should really place the exact fraction, but overall I hope you saw how we might tackle this sort of problem. So let's move on to the next one. You can pause the video and give it a go yourself. Here we go. So from the geometric progression 2, 4, 8, etc. Let's first write an expression for t of n. Well, question A. The first term is 2, and the common ratio, we can see, is just 4 divided by 2. The common ratio is 2. Well, t of n for a geometric progression, it's ar to the power of n minus 1, which will be 2 to the power of 2 n minus 1. Let's do some indices here. This is 2 to the power of 1 times 2 to the power of n minus 1, which is 2 to the power of n minus 1 plus 1. We're adding the indices here. We can just say it's 2 to the power of n. So for question part B, so actually here is an expression for t of n. So t of n is equal to 2 to the power of n. So for part B, how many terms are between 10 to the power of 6 and 10 to the power of 9? So let's take a look if we can find t of n is equal to 10 to the power of 6, or the closest that we can get there. So this would be 2 to the power of n equals 10 to the power of 6. 2 to the power of n came from here. And let's solve for n. I hope you're familiar with your log laws here. So we're going to take the ln of both sides. We get n ln of 2 equals ln of 10 to the power of 6. Dividing both sides by ln2. I'm just going to do some log laws here. This will become the coefficient 6 ln 10 over ln 2. Let's see what we get here. 6 ln 10 over ln 2. 19.93 recurring. So this will give us 19.93. Now, because this is a series, we can't have decimal n values because there's t of 19 and t of 20. Well, t of 19 is less than 10 to the power of 6 because 19.93 is close to t of 20. So this is actually the 20th term. So rounding to the nearest whole for this one. N equals 20 is bigger than 10 to the power of 6. That's the first one. Applying this exact same idea. N to the power of n is equal to 10 to the power of 9. Going through the same process, we get, well, let's skip a few steps here. Going straight to here, you could You know what, let's just go about it. So n ln 2 equals ln 10 to the power of 9. N equals 9 ln 10 over ln 2. This is 29.86. So n is equal to 897. Okay, so remember we want it in between 10 to the power of 9. So in this case, we have t of 29 and t of 30. Now we want it to be less than 10 to the power of 9. So we actually want the 29th term for this. So n equals 29. We don't always go up. We need to really consider what values we need. So the 29th term is less than 10 to the power of 9. And the 20th term is the first one bigger than 10 to the power of 6. So how many terms are in between 10 to the power of 6 and 10 to the power of 9? So this is the 20th to the 29th term. So now, once again, here's where it gets even more confusing. Most students would tend to go, number of terms is 29, take away 20. That's 9 terms. But if, I'm just counting here, if we count them, 20, 21, 22, 3, 4, 5, 6, 7, 8, 9. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 terms. There's actually 10 terms between 10 to the power of 6 and 10 to the power of 9. So, I know this one was rather more difficult, but I hope that gave you an insight into how we could go about doing these types of questions. I'll be putting more example videos out there for you, but overall I hope this gave you an insight into applying what we know to geometric series problems. I'll see you in the next video. Best of luck.